Fuel cells. The previous example raised the question of the possibility of reversible chemical reaction. What is possibility the chemical reaction for fuel cells? Some reactant can be made to approach reversibility by having them take place in an electrolyte cell, as described in Chapter 1. Electrolytic cell. When a potential exactly equals to the electromotive force of the cell is applied, no reaction takes place. When the applied potential is increased slightly, the reactant proceeds in one direction, and if the applied potential is decreased slightly, the reactant proceeds in the opposite direction. The work done is the electrical energy supplied or delivered. Consider a reversible reaction occurring at constant temperature equals to that of its environment. The work output of the fuel cells is W equals LEG bar E where delta is the change in Gibbs function. Delta G, change in Gibbs function. For the overall chemical reaction. We also realize that the work is given in terms of charged electrons flowing through an electrical potential E, W, NE, N0, E. In which Ne is the number of kilomoles of electron flowing through the external circuit, number of kilomoles of electrons flowing through the external circuit. And we can write this relation. electron per kilomole multiply kilojoule of electron is equals to thus for a given reaction the maximum reversible reaction electrical potential maximum electrical potential of a fuel cell at a given temperature. Is delta G and E for the fuses. Here are some example in the chapter and description. A variety of fuel cells are being investigated for use in stationary as well as mobile power plants. The low temperature fuel cells use hydrogen as the fuel, whereas the higher temperature cells can use methane and carbon monoxide that are then internally reformed into hydrogen and carbon dioxide. The most important fuel cells are listed in the table here. When with their main characteristics: fuel cell, T fuel carrier change, charge and catalyst, and the Poisson products. The low temperature fuel cells are very sensitive to being poisoned by carbon monoxide. Low temperature so they require an external reformer and purifier to deliver hydrogen gas. The higher temperature fuel cells can reform natural gas, mainly methane, but also ethane and propane, as shown in the previous table, into hydrogen gas and carbon monoxide inside the cell. The latest research is being done with gasified coals as a fuel and operating the cell at higher pressure, like 15 atm. As the fuel cell has exhaust gas with a small amount of the fuel in it, additional combustion can occur and then combine the fuel cells with a gas turbine or steam power plant to utilize the exhaust gas energy. This combined cycle power plant strive to have an efficiency of up to 60%. A model can be developed for the various processes that occur in a fuel cell to predict the performance. From the thermodynamic analysis, we found the theoretical voltage created by the process at EMF from the Gibbs function. At both electrodes, there are activation losses that lower the voltage and a leak current, shown with I leak, that does not go through the cell. The electrolytic lid or membrane of the cell has an ohmic resistance, ASR, ohmic, current, and ohmic to the ion transfer and does also produce a loss, ohmic resistance. Finally, at high current, there is a significant cell concentration loss that depletes one electronic for reactant and at the other electrode generates a high concentration of products, both of which increase the loss of voltage across the electrodes. The output voltage V generated by a fuel cell becomes output voltage V generated by a fuel cell EMF ASR ohmic minus C Ln leak, where I is current density, ASR ohmic is the resistance, and B and C are cell constant. The current density I0 is referenced I0 reference and IL is the current limit. Two examples of this equation are shown in the next picture. Where for the PEC polymer electrolyte cell, cell activation losses are high due to the low temperature, and ohmic losses tends to be low. Just the opposite is the case for the high temperature SOC solid oxide cell. As the current density increases towards the limit, the voltage drops sharply both cases as shown in these two pictures, and if the power per unit area VI were shown, it would a maximum in the middle range of current density. This results resembles that of a heat engine with heat exchanger of a given size. As the power output is increased, the higher heat transfer requires a large temperature difference, which in turn lowers the temperature difference across the heat engine and causes it to operate with a lower efficiency.